Hello everyone, I am Pranjal Dutta. Today I'll be talking about real tau-Conjecture for sum of squares. Thank you. Thanks to the RCS committee for selecting my work. So we will be talking about the roots of invariant polynomials. Given an invariant d-degree polynomial, how many roots it can have? At most d from the fundamental theorem algebra. But the question is, can you improve it? For example, what about real roots? And it seems we have a better answer. Using Descartes' rule, you can show that an S-sparse polynomial, meaning there a polynomial with S many monomials, can have at most order S many real roots. And the observation is that now if you have two polynomials f and g, or where both of f and g have S many monomials, then f times g has order S many non-zero real roots, which is not hard to show. The question is, what about 1 plus fg? Right? Just you add 1, the multiplication f times g, and it was raised by Arkadev and Koiran independently. Unfortunately, nothing better than order S square is known. So the question is, can we generalize this question? And obviously the question is starting this question has any connection to complexity theory or algebraic complexity theory? So before going to that, there are three important problems in algebraic complexity theory. First to a lower bound question, metric identity and VP versus VNP. They were defined 40 years back by Grigoriev and Valiant. And the third question is polynomial identity testing question, PIT, which is a derandomization question. I'll not be able to define these questions in this short video, but they are well motivated questions and have a close connection to proving P not equal to NP. The goal is that can you come up with a single problem that sort of unify all the three problems, meaning if you solve that problem, single problem, you solve all the three problems. And this is exactly what we do in this paper. We show that there is a single problem which we'll define later, that if you solve, all the three questions will be solved. So to do that, let's just go over some definitions. So we say that f is sum of squares, so is representation if f can be written as sum of fi square, invariant polynomial square, but there are weights ci that is also allowed. And what is the size of f? Size of f is the number of monomials across all the polynomials fi. For example, if you look at 2x plus 2, size of this is 4, and a single polynomial f can have multiple representations. So you take this minimum size across all the representations, we define it as s of f. Now there is some interesting bounds known. For example, s of f is lower bounded by square root of sparsity of f and upper bounded by order of sparsity of f. And the lower bound can be shown just by counting monomials. And the conjecture, now you are almost we can define we can actually state the conjecture in terms of this SF. So for a polynomial f, since there are s of f square many monomials, it can have s of f square many real roots by Descartes' rule. But interestingly, random polynomial f has order s of f many real roots, and we conjecture that actually this is true not only for random polynomials but for every polynomial f, that the number of distinct real roots is bounded by order of SF. Now, if you assume this conjecture, we can show that there are rigid matrices, and you can also prove that VP not equal to VNP. In fact, there is an exponential separation between VNP and VP, which is good enough evidence that P should be not equal to NP. Note that it does not imply P not equal to NP, but many people believe that proving VP not equal to NP is essential to proving VP not equal to NP. And in fact, this also put PIT in quasi-polynomial time by carbonate public. Yes. Yeah. So we'll conclude, and the conclude is proofs sum of SOS tau conjecture for sum of constantly many squares. In particular, start with 1 plus fg that I already stated. Thank you.